All right. Homework question. 46?
46.
I think 46.
Yes, please.
Any others before or besides 46? Okay. Let's do one here real quick. This question came up in our class, and when we were going through stuff during the course of the day, and I'm going to throw a variety of things at you. Some will be on the quiz, some may not, but the ideas are still there as it involves rectangles, Riemann sums, drawing pictures, writing them out, sigmas, integrals, that whole thing. The definition of an integral, which we got up there, which basically says that the area under curve is an infinite number of rectangles added together. That idea. And we're also going to get into some of the story problem kinds of things with units, like number 46. Not that that's a big emphasis on the quiz, but I mean, all a story problem does to the thing is add units into what the function stands for, and so it doesn't really change a lot of what you have to do there. But then, I don't know, somebody came up with an answer, or had a question that they thought the homework all seemed really easy with sigmas and then going into integrals, but they thought that was because maybe all the sigmas just worked out nicely, and that there seemed to be some that we talked about either in the homework or some of the problems that we did up here that made it more confusing. So I thought maybe today we would just start with this one right here. So why don't you take a crack at this one, and I'll just kind of make something up here. Let's say it was this. Let's say you had that sigma right there, and then, of course, I suppose it would make sense to let m go to infinity out here. Okay, so write the integral for that. Okay, a lot of you seem to be somewhat finished, hopefully. I have that much so far. Agree with that? We said some of the stuff we talked about yesterday is we'd identify the width, the 3 over n is the width, and that ends up being the dx right here. And the messy stuff, right, sigma is messy. The messy stuff is where you plugged it, that's the stuff you plugged in for x, so this would be like the x squared. But then the question is, where does it start? And maybe it was this n minus 1 that got some people bothered or something, but how do you know where to start this and where to end it? One good way to do it, and probably the best way to do it, is plug in a 0. And so you plug in a 0 for I, you get 1 plus 3 over n. Now I would probably come over here and do something like this. So 1 plus put in a 0, oh, that'd just be 0 over n, right? So that'd be 1 plus 0, which is just 1. And then if you plug a 1 in for n, you get 1 plus 3 over n. Well, that would be 1 width over, which we would expect that to be the next one, right? So forth, so on. So where does this start? Starting at 1, right? I would agree. And then what? Where does it end? I think that's probably the best thing to do. Take 3 over n. Is that what you were saying? I mean, take the width times how many subintervals? Well, how many do you have here? Isn't there n? When you go from 0 to n minus 1, how many is that? When you go from 0 to 9, how many is that? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You go from 0 to 9, that's 10 terms. So you go to 0 to 99, that's 100. You go to 0 to n minus 1, that's n. Okay, it's n. So if you're going to do it that way, then it would be this. And so then those cancel, and so 3 is your total width. So the total width, so this thing has to end at 4. So this integral would go from 1 to 4. Now the other thing we talked about is taking this top number and plugging it in. And you can do that. You can take this top thing and plug it in. So that would give you 1 plus, and then if you put n minus 1 in here, you'd have 3n minus 3 all over n. And then you split that apart, you'd have 1 plus 3n over n is 3, and then minus 3 over n. Well, that's 4 minus 3 over n, and that's what you expect, because what kind of rectangles are these? These are lefts. When you start with 0 and go to n minus 1, those typically are left rectangle situations. So 4 minus 3 over n, sure enough, that would be your last left edge. It'd be the one that's 1 width away or back from the 4. So again, that tells you that 4 is your right edge. Okay? So it goes from 1 to 4. But remember, we did talk about how you could change this. Wouldn't this integral here be the same thing? Wouldn't those two be the same? If you shift this function left 1, then instead of going from 1 to 4, it'd be 0 to 3, right? And I'm gonna show you a problem where that comes into play here a little bit, where you really need to understand that. But most of the time, so sometimes people look at this as the x right here, just the 3i over n. They think of this function as 1 plus x squared. Well, if that's the case, then when I is a 0, you get 0. When I is a 1, you get 3 over n. When I is a 2, you get 6 over n. So 3 over n, 6 over n, and so then you're starting at 0, right? But the way I did it was 1 plus 3 over n. I used the whole thing as the x, okay, and thought about it that way. Okay, so hopefully that's something we can deal with there. All right, let's take a look at 46 then. Here's the deal with 46. Now, I don't know which part's easier to do first, part A or part B. Write the sigma, write the integral. I think let's do the sigma first. The only reason I would say writing the integral first might be easier is I'm thinking about units here. I'm thinking about the functions. Now, so maybe let's don't even write it as an integral or a sigma, whatever. And let's just think about these functions that are in the problem and think about their units. We have the e function. Now, what were the units on the e function? Kilowatts. And we had the c function, and it was cost per kilowatt hour. Now, you may not have seen a unit like that before, but that's how you write kilowatt hour. It's kilowatt times hour. So kilowatt hour. So dollars per kilowatt hour. All right. I mean, it's the same as dollars per kilowatt per hour. It's kind of like feet per second squared, right? It's feet per second, but then you invert the second, and it's feet per second squared. Well, this is like dollars per kilowatt per hour, but we usually write it dollars per kilowatt hour, like that. All right, and we want to get an answer that is what? What did it ask for? but they want the final answer to be in cost. They want the final answer to be in dollars. So how in the world can I take those and get dollars? That's dollars per hour. How can I get dollars from that? Well, there's two ways to think about it. One way is integral, antiderivative, right? One way we've done it is you take the antiderivative of dollars per hour, that's dollars. So one way to think about it would be to just multiply those together and put those into an integral. And so there you go. But then the other thing I want you to think about here is I want you to start thinking about this. When we put them into an integral, there's a dt there. And what does that dt come from? That's the width, right? That's the width. And what would our width units be in this problem? Our width units would be the t units. What would that be here? It would be hours. So look what happens if you throw that in there. Right? You get dollars. So I would like for us to start thinking about it in those terms too. Yeah, if this is a dollars per hour and we do the integral, that's just dollars. But think of the dx as being hours. Think of that as having a unit, and that also tells you how you can get your dollars out of that. Okay, so there's the integral. So really, we just set up the integral. So that's probably, so part B is probably easier to do than part A. So this would just be e of t times c of t dt. That's going to give us dollars. And then the integral is going to go from what to what? 0 to 24. Because remember, dt, we're in terms of t here, which is hours. So this integral, we want the cost of the electricity over this 24-hour period. So it's 0 to 24. But I want you to think of the integral as an adder. I mean, because that's what the integral is. It's this sigma. And sigma adds up all these things, right? So the integral is the adding process. Okay? Once we get by this quiz, we won't use integral or sigmas a whole lot. We got the integral. The integral is a sigma, right? It's adding up an infinite number of things. So we use the integral as our kind of our adding device if we want to add up a bunch of stuff. Okay, so here we go. So we got this. Now, what would the sigma look like? Well, how many terms were we supposed to use? N. Did it say left or right or anything like that?
Yeah.
It did say left. So then we want this to go from 0 to n minus 1, right? It'd be 1 to n if it's right. We'll go 0 to n minus 1 if it's left. But that's n subdivisions right there. Okay? So we'll pick 0 to n minus 1. Now, I suppose writing a sigma is always easier if you see the pattern. Okay, so what are we doing? We're going from 0 to 24, right? How wide is it going to be then? I need my width. Wouldn't that be 24 minus 0 divided by n, right? So it's 24 over n is going to be my width. So isn't my first left will actually be at 0. So wouldn't this be like, I'm going to use f notation. I know I've got these functions to put it into, but I'm going to just use f to help myself here to start. So won't we start with f of 0 times 24 over n, and then the next one would be f of 24 over n, right? Because we're doing left, so I got to start at the left edge, which would be at 0. Wouldn't it be like this? And then would the next one be 48 over n? Right? Isn't that what I got going on here? The width is 24 over n, and so I go 24 over n, 48 over n, 72 over n, and 96 over n, whatever. Just keep adding 24 over n. Well, what's the pattern? Well, it's now instead of f, I'm going to use the functions I have here. So I'm going to have actually two functions I'm going to have here. Right? So what's going to go in here? 24i over n. Because remember, we're starting at 0, so when we put a 0 in for I, that'll give you 0 for my first one. And then that'll give me, when I put a 1 in for n, that'll give me 24 over n. So both of these are going to have 24i over n. And then what's my width? 24 over n. Right? So it'd be something like that. Be something like that would be the okay, but the only thing, the difference, what made this one a little more complicated, obviously, is that we have these units, we had to put it together. They didn't just give us the function f and then said go. We had to organize it into a function, which was those two functions multiplied together. And we organized it just by the unit. Okay, and that's going to be a very powerful thing. that when we get in chapter 7, all our applications, we really get into the story problem type things. That's how we'll set up integral. I think it ends up being pretty easy, quite honestly. I mean, if you can do it like that with units, you can take a problem. If you recognize that it's going to deal with adding, it's going to be adding up a bunch of stuff. It's going to be an antiderivative. It's going to go from dollars per hour to dollars. You think integral, get an integral in there, and then set them up is really pretty easy. Especially compared to optimization problems, like max min problems and stuff. You guys are going to like them a lot better. You're going to like these a lot better than those. Promise you. But anyway, and then writing this sigma and so forth. So that added a little bit of complexity to the situation. All right, here's what I want you to do. If you get your packets out, the sample 1 and sample 2 packets. Sample 1, sample 2. I went through there and I found some problems that are kind of like the AP test style type things and things we need to be able to do. You know, and it's just the idea. These aren't specific to the quiz tomorrow. I mean, we'll talk about that a little bit later on about some specific things for the quiz. But, I mean, basically, you got to be able to draw rectangles or trapezoids. You got to be able to write them out and add them up. We're going to have some of that here. You got to be able to turn a sigma into an integral. You got to be able to turn an integral into a sigma. Those summation formulas, don't forget about those. But I'm going to give you those on the quiz. You know, I mean, that's it. That's what we've been doing. But here in sample 1, I'd like you to turn to problem. No, let's go to sample 2 first. Sample 2. Problem number 28. It's a multiple choice, no calculator. Why don't you go ahead and give that a try? Do it, you know, think about it on your own a little bit, or then talk with each other if you need some help. Okay, this would have been one we skipped, obviously way back when, but now we should be able to maybe handle it. Got it? There was something a little bit strange on this one, I thought. Actually, I didn't even notice it till I had it already, till I'd already done it. But did you notice anything strange in this one? Oh, yes, that's true. It didn't give it to us as a sigma. There is a sigma here, right? So I think maybe, matter of fact, let me back up here a minute. Maybe it would be best to write the sigma first. Okay? What do you notice with that thing right there? What's that 1 over n? That's your width. I'm going to put it over here. Right? They put that there. Okay? What else do you notice? Well, everything is squared. 1, 2, 3. So that'll be the I over N. All right. Now here's when I finally noticed that something was strange was going on. And to be honest, at this point, I was already starting to write my integral. So the 1 over N would be the Now, hang on. So everybody's really, really quiet. Now, I don't know if that's because you're all just really quiet or if it really worries me that we don't know what we're doing. So the 1 over N is what? There we go. Okay, good. Ooh, I was nervous. That's a dx. And what's this then? That'd be the function. That's the messy stuff squared. Okay, here's where I was getting a little nervous. What should I start at? And go to what? Have we ever had any that did that? Guess what? N doesn't start at 1. N starts at 0. Because what would you get if you started N as 0? I is 0, not N. I. If you started I at 0, what do you get? 0 squared times the width is 0. Can't you see it here? It's hard to see, but it's right there. There's a 0 plus. There's a 0 over N squared plus a 1 over N squared. But it's 0, so they don't write it. Right? They don't write it, but it would be in there. So this actually is N terms. It's just one of the terms is 0, and so they just left it off. Okay? Even if it was just 1 to N minus 1, that would be okay. But here's where you would run into difficulty then is in this part. I can see some confusion here. Like if you put a 1 in here, you say, okay, 1 over N, well, if my width is 1 over N, and I go here, 1 width over from where? 0. So this has to start at 0, and then ends where? Well, if you did your 1 over N as your width, and then how many subintervals? Well, if you go from 1 to N minus 1, that's only N minus 1, and then you might get really confused on what you're doing. But really, it's N in. And so the N's cancel, and so this is 1, total with the 1, so it goes right. Okay? So I think that's a good way to do it. Or you could have put N minus 1 in for I, you get N minus 1 over N, which is 1 minus 1 over N. And you say, okay, that's a left, it's just 1 width short, and it's going to end at 1. So it's 0 to 1. And again, like I said, integrals, your integral is going to be not messy, right? It's going to be clean, tight, neat, whatever. You're not going to have 0 to 1 minus 1 over N or some weird thing like that. Okay, so we're looking at this one here. But here's the thing you got to keep in mind, is that on a multiple choice question, they could have done this to you. They could have not had that even be in there, and they could have given you this integral. They could have had this be one of the choices, and it would have been that, right? Because if you take that integral there, 0 to 1, you shift it 2 to the right, now that would be the integral from 2 to 3. And so they could do that to you in a multiple choice. So you work it out the way you normally would. You come up with your integral. If it's not in the list, look for one that might be a shifted version of what you have. That's what you got to be careful of. Okay? It turns out that this one worked out okay. All right, now go to sample 1 and go to number 28. And it's another one. Give that one a try. are you thinking on that one? Anybody? Another? E. I mean, when you look at this, you got 1 plus 1 over n, 1 plus 2 over n, 1 plus 3 over n, you know, that's I over n. The messy stuff is where the x goes. Now this one's a little trickier because it's not something squared or it's not sine of something or it's not even of something, and so it's like, where was the x? The x, to me, would be down on the bottom here. And that's why I'm looking at 1 over x. Now you look at these. Now again, you got 1 plus, so some people might think of the x just being there, and that's a shift. 1 plus x, that'd be a shift to the left, okay? And so you gotta be, look for that. But if I didn't have these choices over here, I would have called the bottom stuff the x. This is the width, the dx, and then I would look over here on my little x-axis and I would say, okay, the first one is 1 plus 1 over n. Now my width is 1 over n, so that's 1 width over for my left edge. That tells me my left edge has to be 1. And then my right edge, if I got 1 over n times n, that's a total width of 1, right? So this has to go from 1 over here to 2. So this has got to be from 1 to 2. Well, it turns out that that one is there, okay? But, you know, it could have been one of those shifted situations, but that is the one. So, so there's, you know, those were a little trickier because they didn't have the sigma written for you already, so you kind of had to write the sigma, but they were, you know, they had a pretty nice pattern. Matter of fact, that could be a question I ask you tomorrow. Just just give you this pattern and have you write the sigma for it too. We did some of those exercises the last couple of days. So, you know, that's something we want to be able to do, write the sigma. Right, the integral. Of course, they did the limit as n goes to infinity, so this would be just like what's on the board over there. We have an infinite number of rectangles being added up, so that would be this integral. Yes?
So when you wrote the pattern along the x-axis,
Uh-huh.
were you just able to ignore the one on the numerator since it's constant?
That's a great point. I absolutely did do that. Yeah, because here's why. Because this is my function is 1 over x. It's kind of like when I have sine of 1 plus I over n and I write my x-axis, because what's going on my x-axis is just my x, what I'm plugging in for the x. So what I'm plugging in for the x is just the bottom. So that's why I ignore that. Just like I ignore the sine or the e or whatever else is in there when I'm writing it. Yes, very good. All right. Let's see. Next thing I had down here was, all right, in sample 1, which you're in right now, go to the calculator of the multiple choice section to number 37. Here's one that I think we skipped earlier. Now this has a couple of interesting additional things to it that I don't think will be issues for you on tomorrow's quiz, but they'll be good things for us to talk about. But go ahead and see if you can do this one. And again, if you do get stumped, please talk it over with each other. And if you're not sure, you know, ask a neighbor. Now, what's one thing that's a little odd on this one? Anything? They ask you to compute a Riemann sum. That easy? Somebody got an answer? If there's nothing odd, then maybe I haven't given you enough time. Anything? What's that? Anybody stuck there because of a lack of information? Or maybe not even stuck, but notice something's gone? What stuck where, Shelby? What do you just not sure where to go? Could you plot those points? I mean, you didn't know what else to do. Could you plot those points? Right? Make a graph. Okay? And then, let's say you did. Let's say you plotted those points, and then they wanted you to make a, four subdivisions of equal length. What's missing there? What's that? Well, I wasn't even getting into velocity and acceleration yet. You're right, that's a part of this, and so that you could get lost in that a little bit. We'll deal with that here in a second. What's that? Yeah, did anybody find that odd? They didn't ask for 4 left rectangles, or they didn't ask for 4 right rectangles, or they didn't ask for 4 midpoint rectangles? Anybody got an answer for that? They're symmetrical. 2, 3, 4, 3, 2. So did you just start doing one? I mean, that's what I would do if it didn't tell me to do a left or right. I just start doing a right. Now, you know what I mean? Now, I'll be honest, it rarely happens. I mean, this is one of the very few problems I've ever seen where they tell you to do a Riemann sum and don't tell you it's a left or right or a midpoint or something. So there's got to be something up, right? So, but I mean, just start plotting the points. I mean, in blue here I did rights, and on the left, sure, for some of those table values you might need them. All right. So, I mean, okay, so tell me how I would write this first right rectangle. Huh? F, although a function name here is A, but I got you. So it would be f of 2 times 2. Right, yeah. Do what we've done. Right? There you go. There it is. There's 4 right rectangles. Right? A of 2. So in other words, now, so this is what I wanted to do. I wanted to get into looking at tables of data a little more. We did a couple on the homework. We talked about one, I think, a while back. We've done some stuff with tables. But I want you to get a little more, because you may get a function as a table tomorrow. Now, if it helps you, if you have a table, if it helps you to plot the points so you give yourself a graph, because we've done it with graphs and equations, then that's fine. You go ahead and do that. But think about it. Who cares? Remember when I gave you a function f and you were supposed to draw 4 right rectangles? I said, I don't even care what the function is. We just start with f of 2, f of 4. We just find our right edges. Find our left edges. We write it out. It doesn't matter what the graph looks like. It doesn't matter what function it is. And the same thing's true here. All you look at here is you see a table and it's a function a. And so you say, okay, it's going from 0 to 8. So what's my first right edge? 2, and then 4, and then 6, and then 8, right? It's the same thing. It's the same thing. So A of 2 times 2, A of 4 times 2, A of 6 times 2, A of 8 times 2, and then you write those values out. Yeah, so it's the same thing we've been doing. So then what Anna said is really important here because now I get 24. So what happened when I do a right, that means I wouldn't have used this first one, right? So I didn't use the value 2, but I used the rest of them. Well, what happens if you do a left? You'll use that 2, but you won't use that 2. So it's the same. So I wrote out 4 lefts and I wrote out 4 rights, and I did them both, and my hand didn't fall off or anything. It wasn't bad. Okay. Show your work. Write it out. Right. I mean, you don't have to write every step of the way as you do it, but there it is. Comes out to 24. So you circle D and you go on your merry way. Right? Wrong. Baby. Oh, if you did at a midpoint. Yes. What about a midpoint? It says do a Riemann sum. We just said left and right are the same. What about a midpoint? No, it wouldn't be the same. Well, and it actually doesn't have anything to do with acceleration. Here's what it has to do with. They told us that we had to do 4 subdivisions. Since we've got only these 5 data points, how can I do a midpoint? I'd have to know the value at 1, and I'd have to know the value at 3, and at 5, and at 7. Since they didn't give me those, I can't do a midpoint. So I wouldn't have even considered doing a midpoint. It would be impossible. So in that case, when we have a table value, you can only work with what's there. And so if they were going to do a midpoint here, they would have told me to do 2 subdivisions, right? 4 wide. And then I'd use this as one midpoint and this as one midpoint. Okay? Everything go okay? Yeah. That's good. Because I was going to say, I thought your time was quite a while ago. Okay. All right. So anyway, we're just working through some problems here. All right, so anyway, so as I was saying, so we took care of that. That was a good question by Bailey. So I said, so you circle 24 and you go on your merry way. No, Logan. Okay, now let's start talking about the units, right? Now let's start thinking about the units. What are the units on this A of 2 right here? Feet per second squared. What are the units on this 2? Seconds. What's feet per second squared times seconds? Feet per second, which is a velocity, right? So this is what I was talking about earlier. The fact that it's kind of a story problem and we add in units shouldn't really bother us any. It doesn't really have any. It doesn't change anything about how we write out a right rectangle or a left rectangle or any of that stuff. It just gives us some additional information to put some context to what the numbers are. So this is feet per second squared times seconds. Now you also might say, and this is important to understand, whenever you do a right rectangle, left rectangle, or whatever, you're doing an approximation to an integral, right? So if you're doing a Riemann sum or a trapezoid sum, you are doing an integral, right? That's what you're doing. So what we're doing is taking acceleration, doing the integral. Shouldn't that give you velocity, right? Remember, position, velocity, acceleration. If you're at acceleration, do the antiderivative. In a sense, you should be getting velocity. So we should already know that this is a velocity answer we're getting then. 24 feet per second. Now, we also talked about this the other day when we did that problem with the oil coming into the tank. What did we say the integral represented? If you got 600 gallons of oil in a 10-hour period, what did that represent? The change, the amount of oil that came in during that 10-hour period. It's the amount of change. Derivative is rate of change, integral is amount of change. So what this says is in this 8-second period, we gained 24 feet per second of velocity. What Logan's saying is at the beginning, our velocity was 4 feet per second, correct? In that 8-second interval, we gained 24 feet per second. So the question is, what is the velocity at 8 seconds? What's the answer? Tricky, tricky, tricky. The answer is 28. But that points out a really key fundamental idea that we need to have really, that we need to know really well, not for tomorrow's quiz, but for the future, as we go into these applications of integral. For tomorrow's quiz, thank you. For tomorrow's quiz, story problem kind of stuff, not a big deal. I mean, there might be a problem that's got units in it, and so you need to be able to deal with the units, but it's not, probably not this situation, where you've got to understand that it's the amount of change and that kind of thing. That's more important as we go forward, but that's what's going on there, okay? So for tomorrow's quiz, I'd certainly want you to be able to take a table like this, be able to write out a Riemann sum, add it up, that kind of thing for sure, okay? Plot the points if you have to, if that's helpful. Okay, 2011 free response. I don't think I gave that to you guys, so you just have to look up here. Okay? This is from 3 years ago. 3 years ago. 2011 free response. This is question number 2. Calculator is allowed on this one. We have a table of data. It's the function h in degrees. It's a pot of tea that's cooling. It is modeled, they're telling us that h is a differentiable function, so it's a nice, smooth function. Nothing weird going on in between these values we don't even know. And I want to focus on B. Okay? B says, using correct units, explain the meaning of this integral in the context of this problem. Now, I don't even care if you do that last. Use a trapezoidal sum with 4 subintervals indicated by the table to estimate this value. Now, I'll even help you out here. So I would do the trapezoids first, if that's helpful. I'll even write out this thing the way we're used to seeing it, which is this right here. Instead of that 1/10 out in front, here would be another way you could write that. Okay? So calculate this value using 4 trapezoids. And again, plot those points. Make yourself a quick little graph if that'll help you. But you should write out, when it says use a trapezoidal sum, it's expecting you to write out your 4 trapezoid areas. Okay? Go ahead and give that a try. I'll give you a little more time on this one. Anybody got a number of any kind? What do you got?
52.
Okay, 529.5, 52.95, those are both good numbers. Well, hang on here a second. You're partway there. The 529.5 is the trapezoidal sum. Right? But that's just this part. Right? Remember, when you do a rectangle sum, a trapezoid sum, you're doing the integral. So when we do the trapezoidal sum and get 529.5, that is the top number. Okay? Now let's talk unit, and then 10, so what Brenda said is right as well, 52.95. So let's talk about units here, and then we'll get to answering the first part, explaining the meaning in the context of problems. So you see what I did? I went in, plotted those points, drew myself some trapezoids, wrote out each of the trapezoids. Now, you notice that how do we talk about trapezoids? F of x sub 0, f of x1, f of x2, and we talked about how you use the first edge in the first trapezoid. These two are your bases, so that's the 66 and the 60. Now, as we get better at these, my hope is you can just go write this down, would never need to plot these points, wouldn't worry about what the function is. You just take a table and know, hey, I'm going to take 1/2 times my two parallel y values, which are those, times the width. The next two parallel y values, these two times the width. Now, they're unequal widths here, aren't they? One width is 2, the next width is 3, the next width is 4, the last width is 1. But that's the best we can do when we have a table of values. We only use the 66 once, we only use the 43 once, but the others we use twice because they are part of two different trapezoids. And so it writes out just like this. You got to use a calculator, you can add those up, you get that number. But let's think about the units. So what is the height here? What are these y values? Degrees. So when I add up degrees, I get degrees here, and then what's my width? Minutes. So this area, this number here is degree minutes. Remember kilowatt hours? Very much the same thing. This is degree minutes. Now, we can see that in our integral. The h was degrees, and the dt is the time, that's minutes. So right here we can tell this was going to be degree minutes. But then the 10 is minutes. And so minutes cancel minutes, and so we get degrees. So when we do this, this is degrees. Now, what is the meaning? The average temperature of the T over that 10-minute interval. Now it says using correct units, explain the meaning in the context of this problem. So you would have to have all that in there. You would have to say 52.95 degrees Celsius is the average temperature of the T over this 10-minute interval. That's what you'd want to say, because this formula here is something we know as the average value of a function. The average value formula of a function. And so there it is right there. And it's a very common problem that they give you on the AP test. But there's where you might see trapezoids being used. Okay, let's do, well, let's see. What do we got? We got about 30 minutes left, so this will work out about perfect. I'll put a couple of problems up here. Sample 1. You can turn to that one right now, maybe. Sample 1, free response question number 3. Oops, there it went. Come back. There's Shanghai, your old friend. Old friend Shanghai, yeah, there it is. All right. All right. Here it is right here, sample 1, problem number 3, and then I've got now you've got a copy of that one. So this one has got, it talks about minutes of daylight per day, so that's the L. This is actual equation. You can use your calculator, obviously, with that equation. I hope so. And then parts B and C. What is the average number of minutes of daylight? That sounds very familiar to what we were just talking about. What's the total number of minutes of daylight in 1996? And so, so that's a problem we could do. I'm going to put another problem up here. This is from last year's free response. This is table of data, hot water dripping through a coffee maker, the amount of coffee in the cup. So this is ounces of coffee in the filling this cup. And I would point your attention at C here, which is very similar to the one we just did, but it's a midpoint sum. So it wouldn't be a bad little problem to do. Now, I'll put that up here in a second, but oops, I'll put that back up. But let's just talk about the quiz very briefly. So the types of things we're talking about, we had this up the other day. The things we're talking about in the quiz would be, be able to, simple stuff right from the beginning. Draw a rectangle, right? Here's a function, here's a graph, here's a table of values, whatever, plot those, draw a graph. You're going to get to use your calculator. So if I give you an equation, you don't know what the graph looks like, you can graph it on your calculator. And then draw your sketch. If I give you just a graph, draw your rectangles right on that graph. If I give you a table of values, make yourself a graph, plotting those points, draw your rectangles, whatever. Draw rectangles, draw graphs, just be able to do that, be able to write it out. Compare that answer to maybe an integral, by doing an antiderivative, that kind of thing. So that's that stuff. Then also the sigma notation with the summation formulas. We talked about that. You had some of those in the LH packet if you want to review that, where we expanded those out, use those sum formulas. I told you I'd give you those sum formulas on there. I might give you just some simple patterns and have you write the sigmas for them. Okay, and then the integral to sigma conversion, back and forth, that we've been focusing on the last couple days. Turn an integral into a sigma, expanding it out, or take a sigma and write the integral it came from. We talked about this idea here again, how we would, the big thing we learned when we started doing sigmas is that's what an integral is. It's adding up an infinite number of rectangle areas. This is the width, this is the height, you multiply those, that's area. Sigma adds up the areas. This tells you have an infinite number. That's what an integral is. Okay, and I mean that's it. And then maybe in context, maybe a function is given to you in context, like with units, like what we just talked about right there. Okay, so I found a few problems in the review section of the book at the end of chapter 5. I think it starts on page 366 here. Here's a couple more, just some sigma conversion ones. This isn't a full review for the quiz. I mean, you're going to have to go back and look at the pictures you drew, how to draw a rectangle. Hopefully, you don't need to review that much, but how to draw a midpoint rectangle, a left rectangle, a right rectangle, a trapezoid. But in the sigma conversion, doing that stuff, if you wanted some review on that, there's a few problems here on page 366. 50, 53. Oh, shoot. Let me make sure I got this right. 75, 80, 99, 118. So those are just some problems with kind of some sigmas and integrals and so forth. So maybe spend the rest of the time today looking over those. If you want to get those copied down real quick, and then I'll put up that other problem. You got sample 1, number 3. I think that one is not so much for the quiz necessarily, but it's just a good problem to do based on kind of the story type problem stuff we've been doing. And then I think this one in the 2013, where was it? Right here. I think this part C, this is a nice one because you have to do a midpoint. We haven't done a midpoint today. Just make you write out a midpoint sum. But notice there they say 3 subintervals, kind of like what Bailey said. Here we got 6, 0 to 6, but they only asked for 3 subintervals, so you could do a midpoint with that one. So, all right, I'll let you have the rest of the time to work on those things and ask me some questions if you know, any questions you have about the grid. Okay? I did, yes.
I was gonna ask you
Yeah,
just
yeah. The thing that you said on 46 is you just said that the integral would be just be this, and the whole reason was because what the units were. E was kilowatts. C was dollars per kilowatt hour, and DT is the hours. You know, DT is the delta X. And so what happens is you get dollars. So when you put the integral together that way, you get dollars. Then when you do the sigma, it would just be a matter of, okay, it goes from 0 to 24, so our width would be, right, it was n subdivisions. It said do n subdivisions. A left sum, it said do a left sum. So we said that would go from 0 to n minus 1. And the width is 24 over n, so that would be the dt part, right? And then if we were to make like an x-axis that goes from 0 to 24, since the width is 24 over n, the first thing you'd plug in would be that, the next thing would be that, the next thing would be that. So it's just, and well, then you just do your, this is a little different because we have 2 functions, not 1 function like we're used to. But, so that would just be your 24i over n, 24i over n.
Yep.
You know, because 24 times 1, 24 times 2, 24 times 3, all that.
Yeah. Can I like start that please or
You have class work.
yeah.
You think you could do it?
Could I
Pretty much have to do it in one sitting.
I could be late to that class.
No, I don't. Actually, we're supposed to do it outside of class. If you, but yeah, you pretty much need to get it done. I don't want you to be late to class. When else? What other option? Do you have class every class? You have class every class?
Yeah.
So it has to be after school.
Mhm.
After lunchtime. And let's see, which one did you just take? The third one?
Well, actually, I was asking about.
Oh, you're talking about the one for tomorrow.
Yeah.
Oh. Oh, you and I talked about this yesterday.
Yeah.
Oh, okay, yeah. I thought you were gonna, yeah. Oh, jeez. Yeah, because that's gonna take way more than that amount of time. I thought we were gonna do it like right away, like at the start of the month. I mean, you remember when we talked about that, but it was like, if you felt like you needed to review, or, you know, what we talked about, then we would do it later. That's why I said be sure to remind me, because I would not remember. But yeah, I knew we wouldn't just have time here at the end. So you're going tomorrow and
And Thursday.
I was gonna get one,
Yeah, well,
but then I never signed up.
what are our options? Our options would be, is after school an option? After school's an option or next week?
I can just come in after.
Next week? Or after school?
After school.
After school.
I know, that's why.
Okay. All right. See that. Yes, ma'am.
Okay, so I was gone the day that you like assigned these problems.
Okay.
Can you explain these three
Yeah,
sections?
I wouldn't
I
worry
really
too much. I
don't.
wouldn't worry too much about these two sections.
Okay.
Okay. These sections are the ones using the properties that are on page 357.
Okay.
Okay. And so this problem here is, I would take the two out in front. Why don't you bring your book up there?
Okay.
Grab your book and so. Okay, turn to page 357. They're going to be given to you. Sigma is constant, sigma of I, or K, sigma of I squared. So what we can do is we can take this sigma and pull the 2 out in front. And so what we have is a sigma I, which is that one right there. N is that top number. They only work if this starts at 1. Right? So N is that top number. In this problem, N is 20. So this would be 2 times, and what's the formula? 20 times 21 divided by 2.
Oh, okay.
Right?
Mm-hmm.
And so get your calculator out. 20 times 21 is 420. That's your answer. Okay? Next one. Sigma I equals 1 to 20. I minus 1 squared. So we FOIL that out. Get I squared minus 2I plus 1. We'll break that up into 3 sigmas. I squared minus 2. I'll pull the 2 out in front of that one. Okay. Now this is 1 to 20. Right?
So in that one, you have all three of them.
So you use all 3 of them. So this one would be 20 times 21 times 41. All over 6 minus 2 times sigma I, which was 20 times 21 all over 2, plus sigma 1, which would be 1 times 20. And I work that out and get the answer. The idea is that who in the world would want to plug a 1 in, write it down a 2, write it down a 3, write it down, have 20 of these, add them up. And what if this was I to 100? I have to write down 100 of them. These give me shortcuts for it.
Okay.
That's the
That makes more sense.
that's the summation for this. I will give you those.
Okay. Okay. And then these two aren't on. Okay.
That's how we led into that definition as N goes. The only thing about that definition is what I was talking about earlier, how that represents, infinite
Just like how
area.
the
Right,
back
how- right.
Okay.
And not just going back and forth, Shelby, but what I said earlier today, why does this equal area? Because height times width times area, this is adding them up, this means but yeah, you don't have to go through and work through all that.